The animation you are about to see is based on a new home built to the most stringent levels of air tightness and typical to those in the most energy-efficient new homes. This scientific computational fluid dynamics (CFD) research was carried out by the University of Nottingham's School for the Built Environment. As a new home becomes occupied, the central heating is used and the heat from radiators, underfloor heating and other electrical sources starts to rise and accumulates at the highest point in the dwelling. At the same time, each occupant within the home will create around 4 pints of moisture per day, or up to 30 pints of water vapour each week. This humidity triggers the growth in dust mite populations and mould spores, which mix with carbon dioxide, NOx gases and VOCs found in household cleaning products and aerosols. At the same time, the oxygen levels in the homes start to deplete. If you could see the heat distribution along with all of the airborne gases and contaminants in a poorly ventilated home, then it would probably look something like this. We call this a viral soup. The simulation conditions in the property are taken at the worst possible case scenario, where indoor relative humidity is at 100% and outdoor relative humidity is also 100%. The roof tiles on a house often act as solar collectors and will radiate heat into the loft space. According to a recent Energy Saving Trust report, the Good Practice Guide, the average solar gain in a loft space throughout the heating season is at least 3 degrees, resulting in over 550 kilowatts of free energy. The unit is switched on and the fresh filtered air enters the home through the centrally located ceiling-mounted diffuser. The air is introduced along the underside of the ceiling and begins to mix with the warm, contaminated air. Looking at the scale, the CFD model shows that after only 1 hour, the humidity within the dwelling is showing yellow, which means the humidity has fallen to around 80%. After 2 hours, the air has already fallen below 70% and the heat at high level has been totally redistributed around the property, saving energy. After 3 hours, the dilution and displacement process is well underway. The quality of the air is starting to improve as the fresh filtered air begins to dilute, displace and replace the airborne contaminants. After 6 hours, the relative humidity is at 50% and is now stable. The air in the property is clean and fresh. The warm air that is normally lost at ceiling level is being redistributed, making the property much more energy efficient. Another strategy is known as multiple input ventilation. As you can see from this animation, the loft unit is picking up free energy from the loft space, filtering the air and delivering it into the property through multiple ceiling diffusers. The advantage of using multiple inputs is that you can target certain areas of the home where there may be a condensation or mould problem, or perhaps there may be a person suffering from hay fever or asthma. When the loft temperature exceeds 25 degrees, the unit automatically detects this and activates a damper that switches the air supply from inside the loft space to the cooler air from outside the property. The result is all year round whole house ventilation, fresh filtered air being introduced into the property in the most energy efficient way possible. For the past 2 decades, Envirovent have installed over 200,000 mechanical input ventilation systems. The majority are still working effectively and have cost the clients nothing in maintenance. Mechanical supply ventilation is the most energy efficient, cost-effective ventilation strategy that exists. The CFD animation by Nottingham University proves scientifically why mechanical input ventilation is so effective in both airtight and existing homes.